Hi there. Welcome to the lecture for section 6.5, Modeling with Trigonometric Equations. All right, let's begin with solving a couple of right triangles. All right, if we're solving a triangle, what we're saying we want to do is find the angle measure of all the angles and the lengths of all the sides. So if we look at this first triangle here, let's see, we know the length of both legs. We don't know the length of the hypotenuse or the length or the measure of the two acute angles. We do know, however, that it's a right triangle. All right, where should we begin here? Well, it doesn't really matter. We can begin with the first thing that we notice. Since the two legs are given, the length of the two legs, I think the tangent might be valuable here. We know that the tangent of an angle, let's start with angle A, for example. The tangent of angle A, that's going to be equal to, by definition, the opposite side over the adjacent side of the right triangle. So the opposite side is 3, the adjacent side is 7. Right? So we know the tangent of angle A is equal to 3/7. By taking the inverse tangent of both sides, I can then find what angle A is equal to. So the inverse tangent of the tangent of A is equal to the inverse tangent of 3/7. And of course, the inverse tangent undoes the tangent. So A is simply equal to the inverse tangent of 3/7. See if we can find out what that is. Okay, second tangent gives me my inverse tangent, and the argument is going to be 3 divided by 7. And that value is 23.2 degrees. All right, so we have one angle. There we go, 23.2 degrees for A. Let's see, why don't we just go ahead and find angle B next? Now, we could do it in a number of ways. We could use the tangent again and do the same thing over again. Or I might recall from geometry that the interior angles of a triangle add up to 180 degrees. So that means that angle B is going to be 180 degrees minus 90 degrees minus 23.2. Just to vary things a little bit, I think we'll use that approach. So 180 minus 90 minus 23.2 is, let's see, 180 minus 90 is 90. Okay, it's 66.8 degrees. And that's our other angle B over here. All right, so now we know all the angles. Okay, all we need is this length of this hypotenuse. And let's see, I could find that with the Pythagorean theorem, or maybe I could use the sine or the cosine here. I think, I don't know, randomly, let's just use the sine, right? And which one should we use? Sine involves the hypotenuse, so I could use A or B. It doesn't really matter. We've been working with A, so why don't we give B a shot? We'll use the sine of B, and the sine of B is, angle B is actually 66.8 degrees. So we'll say the sine of 66 is equal to its opposite side, that's 7, over the hypotenuse, that's C. Right? Well, solving for C here just involves multiplying both sides by C, right? And then dividing both sides by the sine of 66.8. So we'll have C equal to the sine of 66.8 degrees, which is, let's find out, sine of 66.8. Okay, that's, oops, I missed something, times 7. It's the sine of 66.8 times 7, right? Look, there's that 7 there, or 7 times the sine of 66.8. All right, now let's see what that is. Come back up here, you. That times 7. There we go, 6.4. All right, so the length of side C is 6.4, and now we've solved that triangle. Okay, so we do one more. This one over here, all we have are the, well, we know the hypotenuse and one of the sides. All right, so we need to find the two interior angles as well as the third side. And just to mix things up, why don't we say, let's find that third side first, right? And this time, I think to do it differently, I think I'll go ahead and use the Pythagorean theorem, right? So I can say that a squared plus 10 squared, that's leg squared plus leg squared, equals hypotenuse squared, that's 12 squared, right? So a squared plus 100 is equal to 144. Subtract 100 from both sides. So a squared then is equal to 44. Take the square root of both sides. A will be the square root of 44, which of course reduces down to 2 square roots of 11. And what is that approximately? Let's find out. 2 square roots of 11 is approximately 6.6. All right, so we can now say that the length of side A is going to be 6.6. Does that make sense? Yeah, the hypotenuse always has to be the longest side. All right, now we need to find angle A and angle B. We need trig functions for that. Which trig function? Well, now that we know the lengths of all the sides, it absolutely doesn't matter. Let's see, we've used the tangent, the sine. Let's use the cosine just to do something different. So the cosine of which angle? Let's just say the cosine. Let's do A first. Should we do A first? The cosine of angle A is going to be equal to the adjacent over the hypotenuse, right? So that's 10 over 12, right? So we need to take the inverse cosine of both sides to undo the cosine on the left. So then A is going to be equal to the inverse cosine of 10/12, which is inverse cosine 10 divided by 12, 33.6 when we round up degrees. All right, so there's A, oops, 33.6. What is B? I could use the same method as I used over here and subtract angle A and 90 from 180, or I don't know, just to mix it up. How about if we use the sine to find angle B, just to do something different? The sine of angle B is equal to the opposite over the hypotenuse, right? So the sine of angle B is 10 over 12. Take inverse sine of both sides. B then is going to be the inverse sine of 10/12, which is 56.4 degrees. All right, so there's our B, and we have now solved that triangle. All right, let's take a look at another example. Okay, here we have some tables of values. See if we can find a possible formula or equation that fits the data in these tables. All right, it's going to be a trigonometric function. All right, so there's some x's and there's some y's. All right, if it's a trig function, it's sinusoidal when we graph it, right? It's probably going to be the sine or the cosine, right? Let's see. So what is this data doing? Let's just kind of make a little bit of a rough sketch of that. Looks like the y's go, the lowest value is -2. The highest value is 10, okay? So it appears to me, if I were to do a very rough sketch, I could say -2 is here. 10 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would be up there, okay? And then the x's go from 0 to 6, so 0, 1, 2, 3, 4, 5, 6. Very rough little sketch of this. So when x is 0, y is -2, that's that point there. When x is 1, y is 4. Where is 4? Let's see, 1, 2, 3, 4. It's right there. Okay, so when x is 1, it goes up here to 4. When x is 2, we're all the way up at 10. When x is 3, we're back down here to 4. When x is 4, we're back down here to -2. At 5, we're back to -4. At 6, we're back up to -10. So what does this look like? Let's make a very rough little sketch. And this is kind of what's happening here with this data. All right. So is it a sine curve or is it a cosine curve? Well, it can be either one. Recall that with no transformations, that the cosine curve looks like this. It starts high, goes to the midline, goes low, back to the midline, then up high again. And the sine curve looks like this. Starts at the midline, goes up, back to the midline low, and then ends again on the midline. So this is one period of the cosine curve, one period of the sine curve with no transformations on it. So if I want to write the formula or the equation that fits this graph, I need to decide first, am I going to use a cosine or a sine? Well, let's see. Without any vertical reflection, I think I'm seeing a sine curve here. If I look at this part here, right, trace over that and make it a little thicker. If I'm looking at this part of the graph here, doesn't that look like a sine? It does to me. Here's the midline. Put that midline in there. It starts low, goes high, back to the midline low, and then stops again at the midline for one period. All right. So if we want to write this as a sine, we certainly could. Here's our midline is equal 4. What else do we know? The amplitude, of course, that's 6, the distance between the midline and the high point. The period is, it starts at 1 and it ends over here at 5. So the period is 4. Right? And if the period is 4, okay, we have our standard form for the sine. It looks like this. We could say that f of x is equal to the amplitude times the sine. And in the argument, we have that b, remember this, b times t minus h plus k, where h is our horizontal shift and k is our vertical shift. All right. So if I could follow this standard form up here, I decided to write a sine function. So let me put that in there. What's the amplitude? It's 6, and it's not reflected, so it doesn't have to be negative, right? So I can say f of x equals 6. Now, what is b? Well, if the period is 4, right? If the period is 4, b is going to be 2 pi divided by the period, which is going to be 2 pi divided by 4, or that'll reduce to pi over 2. Okay, recall that, remember those formulas. The period is 2 pi over b. So b is 2 pi over the period. All right, so let's put b in. That's pi over 2. The variable we're using is x. Now, do we have a horizontal shift? Yeah, we're shifting right 1 unit. So we want to say x minus 1. Remember, horizontal shifts are counterintuitive. If we're moving right, we subtract. If we're moving left, we add. We're moving right here, so we subtract. And then we have the vertical shift, which is reflected by the midline, y equal 4, and it's positive 4, so we'll say plus 4. All right, so there's one equation. There's one equation that we could use for this graph, right? If I graph that equation, it's going to look like that. I can do any, but you know the cosine and the sine have that close relationship. They're just a horizontal shift of each other, right? So I could also write this as a cosine, couldn't I? I could also write this as a cosine. So let's see, if I find a cosine curve in here, and I want to stay as close as I can. Whoops. I want to stay as close as I can to the vertical axis. But I could shift it all the way over farther to the right, over to the left. But from what I've drawn here, the cosine that I see without a reflection is this one here. Starts here, goes down here, and comes back up here. Okay, that's the one that I'm seeing with where the whole thing is included here. So I'm going to use that one. To write this as a cosine then, I would say f of x equals, and this is not a reflected cosine, right? Starts high, goes low, then high again. So the amplitude will be the same. B will be the same because it's the same period. But the only thing different here is the shift. All right, with the sine, I was only shifting right 1. With the cosine, look, we're hitting the high point at 2, right? 2 is right there. So we're shifting right 2. Okay, so I would say x, pi over 2 times either I could do x minus 2 and then plus 4. All right? Yeah. All right, so there's two formula. You can write an infinite number depending on how you do your horizontal shift. All right, should we try it one more time? Let's try one more real quick. This one oscillates between +1 and -7, right? So if I draw my graph here, it's going to look something like that, where 1 would be there. We'll say -7 is down there. We're going from 0 to 6. 1, 2, 3, 4, 5, 6. 6 is over there. All right. When x is 0, y is 1. All right, so we're starting high on this one. X is 1, y is -3. Where is that? 1, 2, 3. It's right here. That's our midline. Also, that's halfway between 1 and -7. All right, so when x is 1, we're here. When x is 2, we're at the low. When x is 3, we're back at the midline. At x equals 4, we're back up at the high point. And then it just starts over again. And then 6 is down low again. All right, so there's a, oh boy, that is a very rough, but a little bit of a sketch of what's going on here. Okay, first thing I'm seeing is the cosine, so I think that's what I'm going to write. Here it is, and it doesn't even have to shift. Look at that. That's just a cosine with no reflection and no shifting. So my function here, f of x, is going to equal, my amplitude this time's a little different, right? The distance between the midline and the high point, or the midline and the low point, is 4. All right, positive because we're not reflecting. All right, so it's 4 times the cosine. And what is my b here? I don't know. My b is going to be the period. What is the period? This time the period looks like it's the same. The period is 4. So it's going to be the 2 pi over 4 or pi over 2 again. Same period. All right. Pi over 2x. We have no horizontal shift this time. Our vertical is down 3 because our midline is at y equal -3, right? So we'll do -3. And there we have the formula for this table of data. All right, let's look at some more interesting applications, things we might be able to relate to. All right, here we have a population of elk. This population oscillates 150 above and 150 below an average of 720 during the year. Okay, it hits the lowest value in January. Ooh, so what would this graph look like? Let's see. A little sketch. Let's see. This is over a period of time of a year. They're saying January is t equals 0. So I think we're going to talk 1 year here. So the period then is going to have to be 12. There's 12 months in a year, right? January will be 0, and then the end of December, the following January, will be 12. Let's see, if we divide that in half, that's 6. If we divide it in half again, that's 3. You know. All right, so there's our t-axis. That's going to be in months. Now our y-axis is going to be the population of the elk, right? Or p of t. Yeah, we're going to call that function p. 150 above and below 720. So 720 is the average. That means that's our midline, right? So we'll just make a spot for it. We'll say it's going to be right here. Okay, that's going to be 720. And it oscillates 150 above and below. So 150 above 720 would be 870. And 150 below 720 would be 570, right? Okay. So there's our low point, 570. There's our high point, 870. It's saying that the lowest point is in January. That's right here. So 570, we're there. And this is going to oscillate above and below. So we want to divide this graph up into quarters so we can see what the full year here is going to look like. Right? We know that It doesn't say it, but we're going to assume it's oscillating, that this is a sinusoidal graph, right? So if it's a sinusoidal graph and it goes low, a quarter of the way through, it would go to midway. Halfway through, we would be up at the high point. 3/4 of the way through, back at the midway, at the midpoint. And then at the end of the year, we're back where we started at the low point, right? So that's what our graph is going to look like. Okay, that looks to me like a reflected cosine curve, right? Cosine normally looks like this. Starts high, goes low, ends high. Here we're starting low, going high, and ending low. So I think I want to write this equation as a reflected cosine curve, right? So let's see, it's going to be called P of t, population as a function of time. What is my amplitude? Okay, my amplitude is that 150, right? Because that's the distance between the midline and the high point, or the midline and the low point. So the amplitude, here's our standard formula. Let's write it up here so we have it to look at. We'll say P of t. It's the amplitude times the cosine times b of your variable. We're using t now, minus any horizontal shift, and then plus any vertical shift. All right, so our amplitude was 150, but we're reflecting. See, it's like an upside down cosine curve, so I need a negative in front of it to show there was a vertical reflection there. All right, so it's 150 times the cosine. What is our b? Well, our period is 12. All right, and since b is 2 pi over the period, it's going to be 2 pi over 12, or pi over 6. All right, so there's our period. Pi over 6. The variable we're using is t. Do we have a horizontal shift? No, there's no horizontal shift, so I don't have to worry about h. Right. But I do have a vertical, right? The midline's at 720, so I need to say plus 720. All right, so there's my formula, or my model for elk population as a function of time over a year. Now the second part of this question says, what if the lowest value of the elk population occurred in March instead of January, right? So what is that saying? The lowest occurred in March, 3 months in, here, instead of there. But then it would still do the same thing. So what are we doing here? We're just shifting, put it in a dotted line. We're just shifting our graph to the right, aren't we? Or the left. We could call it the left also. Let's see if I can draw it properly, though. That would be at the midline. Let's try that again. I got off a little. Okay, put this guy back in. At 6, we're here at the average. At 9, we're at the high point again. Okay, there we go. And then at 12, we're back at the average. So it's going to look like this. It would go into the next year maybe. But see what we're doing? We're shifting this graph to the right by 3 months. Okay, so now my h is going to have a value. So here's my January formula. If we started it, if it was changed to March, my formula is going to look like this. P of t equals, now the amplitude is the same. We still have a reflected cosine. So it's going to be negative 150 times the cosine. And b will be the same because the period is the same, right? So that'll be pi over 6. But now it's not just t, and I have to have parentheses here. This is so important, right? I'm doing a right shift right 3, so it's got to be t minus 3. If our horizontal shifts are counterintuitive, then plus that 720. Okay? Things that get overlooked frequently in this course is that when you're doing a horizontal shift, these parentheses here are critical, right? Pi over 6 t minus 3 is not the same thing as pi over 6 times t minus 3. All right, and that's our standard form. So please, please do not forget your parentheses in that. All right, let's look at another example. Oscillating temperature. All right, say the temperature over the course of a day is modeled as a sinusoidal function, right? So it oscillates between a high and a low. All right, suppose you know the high temperature for the day is 63 degrees, and the low temperature of 37 degrees happens at 5 a.m. All right, assume that T is the number of hours since midnight. All right, then find an equation for this temperature, D, in terms of T. All right, so we're looking for D of T. What's our standard form going to be? We don't know yet if it's a sine or a cosine, but let's just write it there. So we know what we have this to keep in mind. A times, I don't know. I'll write cosine. I'll write cosine, but it might be a sine of B times T minus H plus K. Now let's draw a little graph and see if we can think a little bit about what this is looking like. All right, so the temperature is going to be our vertical axis. Time will be our horizontal axis. All right, and we have 5 a.m. All right, so there's 24 hours in a day, right? So let's say our period then is going to have to be 24 hours, right? Our period is going to be 24 hours. And we're oscillating between 37 and 63, so we'll say 37 is there. We'll say 63 is there. Where's our midline? Is there at, let's see, what is 63 minus 37 divided by, let's see what that is. 63 minus 37, that's 26 divided by 2, it's 13. All right, so we're going to add 13 to the 37, that makes it at 50. The midline then is at y equals 50. All right, all we know is one thing. We know that at 5 a.m. we hit the low point, all right? Halfway in between there is 12, and then halfway between those is 6, but it's at 5 a.m., right here at 5 a.m. where we hit the low point, all right? Right away, I already know we're going to have a horizontal shift of our graph here, because if we didn't, we'd have to have a low at one of the quarter points, right, at 6, 12, or 18. All right. Okay, but we don't. We have it here. All right, what does temperature typically do? Well, it's the low point at 5, so it must have been falling before 5 a.m., hit the low, and then it started rising again, right? So it's rising. When is it going to hit that mid point or that average again? Well, the period is 24, a quarter of the period is 6, so looks like it's going to hit it again like at 11. I'm just trying to draw it a little bit accurately. It'd be something like that. Okay. Then it'll keep going to the high point at like 1700, so maybe here. I'm just drawing a rough sketch just so I can see the shape of this, right? Just so I can see it and think about it. And then it would hit it at 23, be back at the average, and then it would just keep going into the next day. So anyway, there's what one day looks like, one period, right? So it looks like. So do I want to try to write this as a sine or a cosine? You know, it doesn't matter because they're just horizontal shifts of each other. I think if I did a sine, I think I would have to do it reflected. The cosine, well, I'm going to have to, I won't have to do a reflected cosine. It doesn't really matter if I reflect or if I don't reflect. What did we do last time? Was it a sine or a cosine? We did a cosine last. Let's do a sine this time. So the sine normally looks like this, right? And if I wanted to not reflect, I'd have to go way over here to start it, which I could, but I could also just reflect it. You know, I could also just reflect it. So I think I'm just going to do reflected sine. Let's choose a sine. What is my amplitude? Okay, well, my amplitude was 13, right? It's the distance between the midline and the high, or the midline and the low. So I'm doing a reflected sine, so that'll be negative 13. We're going to call it d of t. I'm going to put my function in there. Now, what is my period? My period is 24, right? So that means B is 2 pi divided by 24, or pi over 12. All right, so let's put that B in there, pi over 12 times, and do I have horizontal shift? Yes. So what's my variable? That's T is my variable. What am I doing here? I'm shifting either left 1 unit, because normally the low would have been here at 6, but it wasn't, it was at 5. I'm either shifting left 1 unit, or I'm shifting right 5 units. I think I'm just going to do a shift left 1 unit, right? So that means I need to say T plus 1. Counterintuitive, right? Our shift left means we add here. All right, then what is my midline? It's at 50, so I want to say plus 50. Okay? So there we have it. Now we now have a function to determine the temperature based on the time of day. Let's look at another one. Let's look at this temperature problem. Well, the outside temperature, okay, we're still doing the same thing here, but here the low and the high are different. They're 47 and 63. All right, so let's make a little graph of that. The low is 47, the high is 63. Halfway in between them is, whoops, halfway in between them, 63 minus 47, divide that by 2, it's 8. All right, so if we add 8, the amplitude is 8, the midline is 55. Okay, and again, we have a 24-hour day, right? So we can split that up into quarters. It's going to look something like that in military time anyway. All right, so now what do we know, though? We know that this time during the day, the average daily temperature, the average first occurs at 10 a.m. Okay, the average is going to occur at our midline at 10 a.m. So we'll say 10 a.m. is there. There's the 1 point that we know is on that graph. All right, but since we know what temperature does, by 10 a.m. the temperature is rising, right? It's rising. It's going to keep on rising, and if it's sinusoidal, it's going to be quarter. It's going to have the quarter periods in nature, right? But I'll worry about that later. I just want to get this basic shape of this. Okay, so the midline is there. What is a quarter of a period here? A quarter of a period is 6 hours, right? 6 hours before 10 o'clock was 4 a.m. So that means the low point on this particular day occurred at 4 a.m. Okay, and it did something like that. The high point would be 6 hours after 10 a.m. Military time, that's 1600 or 4 p.m. in regular time. So the high of 63 was right there. Then it's going to come back down. 22. Anyway, just the basic shape. It's going to look something like this. And it'll keep going. All right, so I can write a sine or I can write a cosine. It doesn't matter. I could do a non-reflected sign that I'd have to shift right 10. Okay, I could do a cosine and I'd have to shift left. How many? Right? Well, if the low point is at 4. Ooh, that one's confusing me a little bit. Let's see. A cosine looks like that. High, low, high. So we'd have to shift it left somewhere if we wanted to do a cosine. We might as well. Did we do sine last? Yeah, let's do cosine this time then. Okay, so we're shifting left something. I don't know what yet. We'll figure that out though. So I've decided to do a cosine, so that means, and I'm not going to reflect it. So here's the portion of the graph that I'm thinking about here. Let's jot down the amplitude. The amplitude was 8. We're using our standard form again. I'll write it up here. D of t is amplitude times the cosine of b times t minus h plus k. It's a parenthesis. Okay, are we reflecting a cosine curve? No, it's matching, so the a will be positive. Okay, the period is 12, so that means b is pi over 2 again, right? Because b is 2 pi divided by the period. All right, so we'll put that in pi over 12. The variable is t. We definitely have a shift. Let's get those, a horizontal shift. Let's put those parentheses in there. This time, what are we doing? We're shifting left. We could shift right also, couldn't we? And reflect it, or shift right and not reflect it. I don't know. I think I'll just shift left. Shifting left means we need to add. Now, how far are we shifting left? Right? How far? We have to think about that. Normally, the high point would be occurring here at 0. The low point is going to occur halfway through the period, right? Which would have been at 12, right here. But it didn't. It occurred at 4, right? So that means we're going to have to shift this right 8 units. Shift it right 8 units. Or shift it left. Or shift it left 4. I think I want to include, I'm not going to include we're going to shift right on this one. So t minus 8. That's the only way that we can do. No, it wouldn't be 8. It would be 16. So I could do t minus 16, but that's a lot. Let's go shift left. Shift left, we only have to go left. It's normally at 4. It would have to be normally at 12. We have to go left 8. Because it doesn't matter. We have to do 8 no matter what. If we're doing a cosine. Sine, we wouldn't have to shift as far. That's okay. So t plus 8, but we've got that vertical shift as well, so we'll have to say plus 55. Okay, so there's an equation that we can use for this graph. Now, the second part of this question is saying how many hours after midnight does the temperature first reach 51? All right, where's 51? It's about somewhere in here, right? So where is it first going to reach it on the graph? Right here in this day. All right, so how do I find that? We know it's going to reach 51 again later on in the afternoon, but I want the first occurrence. I'm going to need to solve the equation, right? I want to say 51 equals 8 times the cosine of pi over 12 times t plus 8 plus 55. All right, and let's solve. All right, we'll subtract that 55 from both sides. So negative 4 is equal to 8 times the cosine of pi over 12 times t plus 8. All right, now let's divide by 8. Okay, so then negative 1/2 is equal to the cosine of pi over 12 times t plus 8. Now we're going to have to do a u substitution to solve here, right? Because the argument of the cosine is an expression. So we're going to let u equal pi over 12 times t plus 8. Okay, and we're going to solve. So negative 1/2 is equal to the cosine of u. All right, so that's actually on the unit circle. Or I could use the calculator for it too. I can use the calculator. U would be the inverse cosine of both sides. So u is the inverse cosine of negative 1/2. Let's let our calculator tell us what that is. Okay, the inverse cosine of negative 1/2, or 0.5, It's 120. Oh, we're in degrees. I want to go back to radian modes here. Unless we're dealing with triangles, we usually use radians. So let's switch this back to radian mode. There we go. Click from there. And let's just enter that again. Second entry and then enter. There it is. It's 2.0944 radians. Okay. All right, so that's the angle measure. The angle measure. It's not what we're looking for, though. We're looking for the time, right? We're looking for the time, so we're looking for t. So now we have to undo the substitution. Okay, since u is equal to pi over 12 times t plus 8, we want to say that, oops, I don't know what that was. Make that bigger. We want to say, that's supposed to be a 4 there. We want to say that 2.0944 is equal to pi over 12 times t plus 8 and solve for t. All right, so we'll multiply both sides by 12 over pi. Let's see if I have room here. Okay, to get rid of that. So 12 times 2.0944 divided by pi. Let's see what that is. All right, so 12 times that answer divided by pi. There's pi. And the answer is 8. Okay, so let's rewrite that. So then 8 is equal to t plus 8. No, I did something wrong here, didn't I? Oh, no, I did. This should have been t minus 8. Oh, I got the wrong sign there. Oh, my goodness. All right, let's fix that. That should be t minus 8 for a shift right, shouldn't it? Or yes, I did a plus. Well, it should have been a minus for a shift right. Okay, so there we go. That's better. Now this is going to work. So 8 is equal to t minus 8. Add 8 to both sides. T equals 16. That's not when it's first occurring either. So where's our error? We got some kind of an error going on here. Let's see. Look at my notes here. Oh, that's not 8. That's 10, isn't it? Let's see. No, that's right. 51. I have the shift wrong. The shift is not 8. All right, let's see. The shift, so it's at 10 a.m. The average, oh, I did it with a sign last time. This would have been easier with a sign. The shift here is wrong, though. It shouldn't be 8, should it? Yeah, let's see that as being a problem. Last time I did it with a sign, and I did a shift of 10, which was easier to see. Look, there's where the sign goes with a shift right of 10. With the cosine, it should be fine, except that it's not 8, is it? It's 6, isn't it? No, 10. Yeah, it's 6. I counted that shift wrong there. Counted that shift wrong. All right, let me show you how I did it the first time, though. It was easier to see the cosine. Let me just give you the right, or the sine. Let me give you the numbers that are right on that. With a sine, we shift right 10. Okay, so here's the sine guy. See him? And he's easier to see that he's shifting right 10 because look, the average first occurs at 10. I didn't draw it very well, but the average first occurs right here at 10 a.m. So I think I unwisely chose the cosine here and got my shift wrong. It should have been 6 with the cosine. But if we switch it over to a sine, easy to see that that's a shift right 10 because that's where the sine begins, right? That's your basic for the sine. It looks like that with no transformations. All right, and then everything else would say the same. Now when we redo the math here, this is shift 10, change him back to a sine. All right, sine here, and a 10, and that's a 10. Okay, so now negative 1/2 is going to be the sine of u. All right, and the sine of negative 1/2. Well, the inverse sine, we'll do inverse sine of both sides. The inverse sine of 1/2 is, come on, come back. There it is. All right, inverse sine of negative 0.5. There it is. It's a negative, which is down below, and that should be fine. Okay, so it's a negative 0.523. We want the first occurrence, so that's right. So it's a negative, let's put that in there, negative 0.5, what was it? 236. All right, now do the same math, multiply both sides by pi over 12. So now we're going to do, that's a 10. Now we want to do 12 times negative 0.5236. And actually could even use the more accurate on this, but it'll be all right. Divided by pi, 12 times negative 0.5236 divided by pi, and we get negative 2. All right, add 10 to both sides. We get the time at 8 a.m. and 8 a.m. fits our graph very nicely. It's like a little bit before 10. All right. So I apologize for the error, but it was actually kind of a good thing. The reason I made that error was I didn't choose the clearest graph, right? It's easier to see that sine function here than it was the cosine function. It was too much of a shift. There wasn't enough of it showing. So the point is, look for the easiest graph. All right, there is one more. It's after midnight. Okay, we got that. So there is one more application that I wanted to show you. I want to come back to our Ferris wheel application. All right, remember that one? All right, so here we have a Ferris wheel. It's 45 meters in diameter. Let's try that again. That looks more like a Ferris wheel. Okay, so it's 45 meters in diameter. It's boarded from a platform 1 meter above the ground. Okay, so there's the ground. That's 1 meter. All right, the 6 o'clock position is level with the loading platform. Okay, I've got it drawn that way. All right, and the wheel completes 1 full revolution in 10 minutes. All right, that means that the period is 10 minutes. Okay, the period is 10 minutes. How many minutes of the ride are spent higher than 27 meters above the ground? Well, all right, so we're going to have to write the equation here, write the formula for that. So let's graph it and decide if we want a sine or a cosine. We start low, start at 1, and we go up to the top of this is going to be up here. It's going to be 46. 1 plus 45, right? We start low, we go high, we come low again. That looks like, let's see, and halfway through, we're at the high point. Okay, so it's going to look something like that. That looks to me like that's going to be a reflected cosine, right? Cosine normally does this. We're reflecting it. Okay. Now the midline on this halfway point here will correlate to the radius of the circle plus where we're starting from. So the radius of this circle is going to be 22.5, right? So the midline is 22.5 plus 1, or 23.5. All right. The amplitude is the 22.5. That's the radius of the circle, or this distance here. It's going to be the amplitude. All right, so let's see if we can write this. The period, well, what's the period? The period was 10. All right, let's find B first. So B is 2 pi over 10, or pi over 5. I think we have everything. All right, so if we want to write an equation for height above the ground, we'll call that h as a function of t. It's going to be an amplitude of 22.5, but it's reflected. So negative 22.5 times the cosine of b, that's pi over 5. And there's no horizontal shift here. Okay, so pi over 5 times the variable. We're saying the variable is t for time. Okay, and then the midline is 23.5. So we'll say plus 23.5. There's our equation. Now we want to use that equation to find how many minutes the ride are spent higher than 27 meters. All right, so we'll say 27 meters is, I don't know, maybe about right there. All right, so what we're looking for is how long we're on this portion of the graph here. Right, that's 5 minutes. So we're going to need to find two values this time, the first and the second occurrence. Right? The first time when we're coming up around the circle, and the second time when we're coming back down. All right, the height that we're interested in is 27 meters. So we're going to say 27 equals negative 22.5 times the cosine of pi over 5t plus 23.5, and we're going to solve for t. All right, let's isolate the trig function first. So subtract 23.5 from both sides. So negative 3.5. Is that right? Negative 3.5 then is going to equal negative 20. Oh, not negative 3.5, just positive 3.5. All right, it's going to equal negative 22.5 times the cosine of pi over 5t. Okay, then we'll divide both sides by that negative 22.5. And we will have isolated the trig function. All right, so negative 3.5 divided by 22.5 is going to equal the cosine of pi over 5t. Okay, we're going to need to make a u substitution here. So we'll let u equal the pi over 5t, right? So then negative 3.5 over 22.5 is equal to the cosine of u. Now let's solve for u. So I'm going to need to do the inverse cosine of both sides. So then u is equal to the inverse cosine of negative 3.5 over 22.5. And let's see what that is. That's going to be our first one. So we'll call him U1. All right. Inverse cosine of negative 3.5 divided by 22.5. There we go. It's 1.7270, we'll say. Let me round that. Okay, so that's just the first occurrence. Now we need to look at that in the unit circle to see what our second occurrence is going to be, right? So let's see, maybe I can put my unit circle up here. The first occurrence, so cosine, inverse cosine is restricted to quadrants 1 and 2, and the 1.727 radians is over here in quadrant 2, right? So there's our U1. It has a negative cosine, like the x-coordinate is negative, and it should be, because it's left of the vertical, right? Whatever that is, that negative 3.5 over 22.5 is the x, the y is something. So where does the second occurrence of this angle occur? Where the cosine is the same, right? So there's another one that has the same x coordinate over here, whatever that negative 3.5 over 22.5 is, and the y will be whatever it is but negative of it, negative y at this one here. So there's two angles. Here's U1, U2 is this guy all the way around there. That's our second angle. All right. So how can we define that second angle in terms of the first angle? If I could find the reference angle and add it to 180, but there's an easier way. Look, isn't U1 equivalent to that angle that I just drew there? Yep, those are equal. So I can then say that U2 is 2 pi minus U1, which of course is 2 pi minus the 1.7270. So there's my two angles, but I really don't want those angles. What I really want to find is that time, right? T. So I've got to undo my U substitution. Now we're out of room, so I'll come over here to do it. All right. So U1 was 1,000, or not 1,000, 1.7270. And that's going to be equal to that pi over 5t. We'll solve for t. We just want to multiply both sides by 5 over pi. Because then that all divides out. And we see t, our first t, call that t1. It's going to be 5 times 1.720 divided by pi. There it is, 2.7375. So 2.7375 minutes after the ride starts, we first hit the 23.5 feet, or no, I'm sorry, the 27 feet above the ground. Now, what is the other one, the T2? Well, then we got to take U2 and solve that. So it's 2 pi minus 1.7270 equal to that pi over 5t, right? So multiply both sides by the 5 over pi. Divide all this out. And our second t, our t2 then, is going to be, let's see, that's going to be 2 pi minus, there it is, 2 pi minus 1.7270. Okay, then times 5 divided by pi. And there we have it, 7.2514. Okay, so at 7.2514 minutes after the ride starts, we hit 27 feet again. All right, so how long are they in the air? We'll just subtract them. 7.2514 minus 2.7375. What is that? 7.375. It is about 4.5 minutes. Okay. So there we have it. The riders of this Ferris wheel were above 27 feet for about 4.5 minutes. Okay, that ends the lecture. The last section in 6 here, applications of trigonometric functions.